You as well, Clay, while muted. Sorry about that, but I did get your testing center preference listed down. And as promised, we're always going to start right at 6 o'clock. That way you're never going to feel like you miss anything. You've come in right on the hour. Welcome back, everyone. I hope you had a fun holiday for Labor Day. Today is going to be our first, pretty much a full day, not giving a whole lot of announcements of those kinds of things. And we do have a pretty good set of things to cover today. We may not complete every single one of these sections, but we are a bit behind on the syllabus. We'll get caught up back to where we are at. And that's another thing to mention about this particular class. Oftentimes, if you look at the day-by-day syllabus for our schedule, we're often covering multiple sections on a single class meeting. So does feel like a pretty fast-paced course, but it's a reasonable amount of work, and it does slow down once we get a little bit further on in. But before we get started, back to section 2.5, we're on example 1. Anyone have any questions or comments for the class to start us out? Okay, let's get started then. So we're back to section 2.5. And we really only just got started talking about solving linear inequalities in this section. Our goal is to solve inequalities that look like this one here. Let me zoom in a bit more. But before we get to solving something like this or something like this on either part, we have to know how to handle once we get to this step, once x is isolated totally alone on one side of the inequality or the other. There's a couple ways we're going to write down our answer. One way is the so-called graph. Oftentimes that'll be something asked. Another way to write our answer is going to be an interval notation. And the third way to write our answer is really just right over here. This is referred to as the inequality form. Which is often the last step when we're solving the larger inequalities like the ones we were looking at the bottom of the page before showing the graph and then the interval notation. So 3 ways to write down our answer, but that's all useful different ways of visualizing the information. Because after all, saying x less than -3 is really a big idea. We're saying it's every single number whatsoever, excluding -3, but to the left, as in going to the left to -4, -5, or sometimes we might say large negative numbers. The negative infinity says there's no stopping point, there's no bound. And this is how we visualize the inequality x less than -3 as a graph. Trouble with the graph is that it's a lot to write down. So if we want to have a shorthand of the graph, this is what it looks like in the green here in interval notation. We match up the same order things appear. The negative infinity would come first. Instead of shading an entire number line, we drop just a literal comma. So that represents the shading. Then we go to an upper bound, -3, and stop there. Well, other big idea is watch how these symbols track. If we say less than, that means we're not including -3 as an answer. So we remove it from the graph with the open circle, and we remove it from the interval notation with the parenthesis. Now, keep that thought in mind. If it's less than or equal to, that means the number is included as a solution. 19 solves this inequality. So we put a solid dot to say 19 is part of the graph. It's also a solution. And we put a bracket to say 19 is part of the numbers in the interval notation. So 3 different ways to say 19 is included. three different ways up here to say -3 is excluded. That's a lot to keep in our heads all at once, but we will be practicing this in sections 2.5, 2.6, and 2.7. 2.7 has been split into two sections, similarly as well in the homework when you go into the Newton system. So parts A and B was kind of a warm-up. We're going to add to this on part C. But any questions first with this warm-up review problem here? Okay, well, just a rundown. We said on part A, x is less than -3. On part B, we say x is greater than or equal to 19. And now x can be between numbers. So here we have x is less than or equal to 1 and less than 3. So it's between 1 and 3, 3 excluded, but including 1. Let's graph that out and then write down the interval notation. So first starting with the graph. We have to be really careful with the signs that we see. The less than or equal to means when we go to put a 1 on the number line, here's 2 and here's 3. We're going to start with a solid dot. Let me match up the solid dots we did up above. Solid dot is going to match up with the less than or equals to. So this conveys over here in this way. Then we start shading up to 3. But right at 3, we have to put in an open circle to match up the less than, strictly less than inequality. So there'd be an open circle there. That's kind of a big one. Shade in between in this way. And this would be our graph this time. Once we have a graph, we're ready for the interval notation. But it's all a matter of just reading left to right. Remembering the solid dot goes with the bracket, an open dot goes with the parenthesis, and I actually wanted to add one more arrow. Just as a reminder that the less than here went to the open dot there. So read this graph here going left to right. Here with the solid dot, start with the bracket, place in the number 1. Shading just turns into a literal comma, like we said. So there's the comma. We go up to 3, and we stop there. 3 is not part of the solution set, so we just put a parenthesis to convey it. So that's the interval notation below. Interval notation is sometimes kind of hard to get a handle on, especially if you feel really rusty or really new to this kind of stuff. But just remember the trick of solid dot to a bracket, open dot to a parenthesis, and the fact that you're just rewriting what you see in the graph, going left to right. In fact, when you go to do these in homework problems, sometimes all they want is the interval notation. But when you're writing this down on your notebook or your scratch work, it's a good idea to do the graph first because we have to learn both. And if once your graph is down, that's the easier one to put down. You can just copy down the interval notation based on what you see above. So it's a great way to learn these all at once. Well, we did it, folks. That's example 1. It's been a long holiday, long weekend, so we're about 8 minutes in, already on our way. Any questions before we try the next one? Okay, so let's take a peek at what we're getting into next. Example 2 are some of the bigger problems that you're going to see in this section on solving inequalities 2.5. This one has a strictly less than, so let's copy this just for a moment. Just as a reminder how all this goes together. We'll take another look at this when we finish this problem up to see how we did. So now instructions say to solve the inequality. These are the full problems. The red here means I did make a change. I felt like this was more interesting of a problem with a negative sign there. After we solve it, we'll plot the solution set on the real number line and then do interval notation as well. So just as before, let's see. We'll use that color for the number line, and interval notation we'll do in that color, just like above. But the very first thing is you proceed as if you were solving an equation. Like if there was an equality sign right there at the red dot. The whole goal is to get x alone. So proceeding like before, we'll add 1 to both sides, just like if it was an equation. We have negative 3x. Don't forget to copy everything down. Sometimes a copy error like I just about made is one of the easier mistakes to make in algebra. Add together on this side, and we have less than 5. Then the next step some people might be anticipating is tricky because we're dividing by a negative sign. Let me rewrite this one more time so we can see what the prior step looks like. We have negative 3x and 5. There was a less than sign there, but we're doing a new step. We're getting x alone, so we're dividing by negative 3 on the left, dividing by negative 3 on the right. So when we divide by a negative sign, anyone recall what would happen in the middle here? Kind of tricky in a way. If you're not sure, that's all right. That's kind of the purpose of this class. Let's pause right here and think about this with a simpler example. This is one of the ways that inequalities can sometimes be a little bit more tricky. We started with something like negative 3x less than 5. But what makes it hard to really see what's going on is the variable. Let's say we had something else going on. Maybe, say, negative 30 less than maybe, how about 20? Slightly bigger numbers, but the major feature here is the fact that there's no variable, so it's easier to see what's going on. Negative 30 is definitely less than 20. But now we imagine we did something like this. Let's divide both sides by negative 10. Negative 30, divide by negative 10. 20, divide by negative 10. So if we divide both sides by a negative number, well, the left-hand side is now equal to a negative divided by a negative is a positive, so that's a positive 3 on the left. Over here, a positive divided by a negative is now negative, so this is negative 2 on the right. And notice something has happened. If I put a less than symbol in the middle, it's not true, because 3 is bigger than 2. Bigger than negative 2. So this actually flips signs out of nowhere. And that's the thing we have to be really mindful of. Let's make a note out of this. When we divide or multiply by a negative number, the inequality sign flips. Deserves an exclamation mark. So right up here, when we had negative 3x less than 5, but then we had to divide by the negative sign, this flips as well. It's now a greater than direction. This red just to emphasize, not to say we made any mistake. This is the trickier part or more frustrating part about dealing with this exercise set. But once we've done that, the negative and the negative will cancel. We have just x is greater than negative 5/3. I notice what I did with that negative as well. You could keep your negative in the denominator, or you can move it out front in the fraction, or you can move it up into the numerator. Either way you visualize it, you're looking at the same exact number, negative 5/3. Well, this is the inequality form, so this is like 1/3 of our answer. We also want the number line solution and the interval notation solution. Any questions so far, folks, getting down to this form? Okay, let's start writing this out. Starting with the real number line, first thing we put down is this cut point, negative 5/3. This is what cuts off the solutions and the non-solutions. Then we observe the format of the inequality sign. This is what we call a strict inequality because it says just greater than. It doesn't say greater than or equal if it looked like that, for example. That means there's an open circle. We also have to be really careful with this one. Let's look at our solution from part A, example 1. When we set x is less than -3, well, that just means we shade to the left. These are all the things smaller than or less than -3. But now when we say x is greater than -5/3, we shade to the right now. These are all numbers strictly bigger than -5/3. So the shading goes this way. This is the next thing that can be a little bit extra tricky about this kind of problem. Again, you don't have to shade in the arrowhead, that's just for emphasis. Watch out for the directionality. If we have an x less than -3, it's just to the left where you shade. But if we have x greater than -5/3, we're shading to the right in this way. At that stage, optional if you'd want to put an infinity or not on paper. I usually put it just for effect to help with interval notation that comes next. But this is pretty much the fun part. We're just about done. We go here. Starts with the open circle, so we start with the parenthesis in interval notation. Put in -5/3, comma, infinity. At this stage, we're completely done. That's our full solution. Answer in 3 different formats for this original inequality up here. Any questions at all, folks, getting through either one of those portions of the solution? Fixing some of my penmanship here. Okay, let's try out another one. And this is pretty much the punchline section 2.5. I think our first section of the course was a little bit tricky because there's a lot of different kinds of problems. But this is more focused. We're just solving these kinds of inequalities in their various formats, giving these 3 different kinds of formats for the answer. The homework set isn't always going to ask for every single portion, sometimes just the interval notation, sometimes just the graph, for example. But it's good to practice all 3 because all 3 can come up, say, in an exam setting. So let's try out another one. One thing I try to avoid doing when I write these notes is just do all the easy problems. So occasionally on my notes, I'd like to select something that looks like this. It looks like it's just not the funnest problem in that section. And so I try to do some of the more challenging ones as well. If you're ever doing homework and you feel like there was one in there that was extra challenging, but we never really got to, don't hesitate to ask about it at the start of class. Copy it down in your notebook. I might ask you to read it out for us, but that'll only take a moment. And then we'll solve it in class. Or if you prefer, you can just take a screenshot or a cell phone picture of your screen, anything like that. Send it to my email and you can say, hey, Mike, this problem was awful. I hated it. Could you take a look at it at the start of class? And I'd be happy, very happy to do that. Here's one of those kinds of problems. So the nastiest thing about this, well, there's a couple things that are nasty. First, there's like terms on the left-hand side, 3/5 x, -1/2 x. Second, x is on both sides of the inequality. There's 1/5 x on the right-hand side. But really the big third thing that makes this kind of annoying is the fact that it's got denominators. It's okay, we'll handle these kinds of stuff as we get through the course. It's not our first time seeing something like this in the course already. The strategy here is when we look to the denominators, the factors are 5 and 2s, that's all we see. So we want a least common denominator. What we're going to do is, once we find the least common denominator, is just multiply both sides of an inequality by that value. The least common denominator is, we might as well define it here, smallest number all denominators divide evenly into. So 5 and 2s aren't too bad. If you thought 20, it's not a bad idea. 5 divides 20, 2 divides 20. It's a common denominator, but it's not the least common denominator. The least in this is probably the most important part. This is often abbreviated as LCD, if you recall that. The least common denominator means you'll do the least amount of work, so it's extra special in that sense. Anyone happen to see what the least common denominator is for this particular example? If you're thinking 10, you're on the right track. Let's think about why 10 works. 5 would divide it into 10, evenly going twice. 2 goes into 10, evenly going 5 times. And it's really the smallest number. You could think 8, but 5 won't divide into 8 evenly. You might think 5, but 2 doesn't divide into 5 evenly. This is the best we can do. If we use the least common denominator of 10, we can multiply both sides by that factor 10 and clear out all denominators. Any questions at the moment? Okay, so this is what that step is going to look like. First thing I'm going to do is just write down the whole inequality. That way I don't write too much stuff on the original question, makes it kind of hard to read. Then let me actually give us some color coding so we can see it better. Let's go for purple, why not? It's a good idea, so it needs a color that stands out. This common denominator is 10. So multiply everything on the left by 10. Then we use that mantra from algebra. What you do on the one side of the equation or inequality, you do on the other side. So multiply by 10 into every numerator on the right-hand side. So now every single term has been multiplied by 10. And now we start simplifying things down. First, we know 5 is going to divide evenly. That's the definition of the least common denominator. It was the number every denominator would divide into, and it's the smallest such number. So we want to start canceling now. 5 divides into 10 going twice. All that's left is 2 times 3 times x. So 6x on that term minus, then just rinse and repeat. This is kind of the fun part because now we're hacking things down, eliminating denominators. 2 divides into 10 going 5 times. So it's 5 times negative 1 times x. So just a negative 5x is greater than or equal to, and keep on going. 5 goes into that 10 twice. That's kind of an exaggerated slash mark. Let's keep it kind of tame there. So this is just 2 times 1 times x, so 2x. Then finally, 2 goes into 10 5 times. So this is just 5 times negative 1, so negative 5. So what we've achieved here is we took an inequality that looks really annoying. It's got too much going on, and we just exchange it for this one. It still has a lot going on, but
Do we add 5 to both sides to cancel out the negative 5s?
yeah, absolutely. We can add 5 to both sides as our very next step. We can also add this 6x minus 5x together. And those would be the very next steps we do, absolutely. Other questions at the moment? Okay, let's take that actual step. First, I want to combine these two together. By 6x minus 5x, they're like terms, so they would just add up to 1x or just simplify to x, greater than or equal to 2x minus 5. And then let's take that step that you mentioned. We can now add 5 to both sides. Add 5, add 5. Now 5 and x are unlike terms. There needs to be a 5x here to combine it with x above. So we just simplified the left-hand side as x plus 5 greater than or equal to 2x. It's getting better. We now have 5 on the left side, but we still have that one problem I mentioned. X is on both sides. But that's okay. You could subtract x from both sides, or you could subtract 2x from both sides. All roads you take is going to lead to the answer. Let's go with subtract x from both sides in that way. That'll take us down to here. X and x are like terms, they just cancel. Now it's 5 greater than or equal to 2x minus x is 1x, and 1 times x is just shorthand for writing x. And that's our solution in inequality form. Might look kind of funny, right? Because x is on the right-hand side this time, and that's okay. You can leave it like that if you like, or you can just take the whole thing and flip it around. Whichever direction the inequality is pointed to, just make sure it's pointing to that same thing when you flip things around. So if you don't like 5 greater than or equal to x, the way this reads, you can move thing x here, move 5 here, change this direction. And if I read this right to left, it would still say 5 is greater than or equal to x. But in English, we usually read left to right. So now it reads x is less than or equal to 5. So either answer is completely fine. If the system asked you for inequality form, it knows that this one is just as correct as this one. But oftentimes I would take it to this step just because we're used to seeing it that way, right? That's what we were practicing up above here. So that's a step I usually would take personally. Any questions at all, folks, with this step so far? Okay, just 2 more things about this problem. We also want to go here and graph it. So I'm going to maintain the color coding for the graph and interval notation on all these notes, just to have some consistency. When it says x is less than or equal to 5, put 5 on a spot. Doesn't matter where you put it. You can put it directly in the middle. That's what I would often do. And less than or equals means you're shading to the left. But maybe before we do any of that, it's good to have a system or a process. The very next thing we would do is decide on an open dot or a solid dot. Anyone recall which version we would have to use here? Is it open or solid at 5? Sounds like it's still kind of a tricky concept. If you've seen this for the first time or you feel very rusty, that's kind of understandable. Let's take a look at it one more time above here. One thing to always keep in mind is the greater than or equals to is always going to line up with the solid dot, which is just a way to convey the number is in the set. And it'll line up down here with the closed bracket, the angled bracket is a better way to say it, rather than the open parenthesis here. I notice we often say open parenthesis because we're also looking at an open circle. Closed filled in dot, we often say closed bracket to go along with it. So back down to the problem. If it's less than or equal to 5, that means we have a closed dot right here. There it is. And less than direction, less than or equals to, means now we shade going to the left. So all numbers in this entire region, infinitely many such numbers, some of them not too big, like 3, some of them really, really large negative, like negative 10 billion, go into the set. Negative infinity isn't one of those numbers in the set. It's just a concept to say it goes to the left, never stops. There's no boundary where our solutions would end. Then finally, interval notation, like we mentioned, is just a way to write this down really fast. It's nothing but a shorthand. So we would always go a parenthesis to match up either one of the infinities. A comma takes the place of the shading. And if it's closed here, we would use a bracket down here. So we did it, folks. That's our interval notation for this problem. Well, that's pretty much all I have to say for the major concepts we're going to see in these notes. Any last questions or comments at all before we take a look into the next section? Okay, let's save these up. And now we're off to our next adventure, section 2.6. 2.6 and section 2.7 coming up next really is just building up these kind of concepts. We're still solving inequalities, but as the name suggests here, they're compound inequalities. So a little bit more going on. What makes them a compound inequality in this section is we're handling more than one equality at the same time. So we want to solve this, find the solutions, solve this and find the solutions, and take the set of solutions that solves both inequalities at the same exact time. That's only if it's an and. If it's an or, that means we take whatever solutions are on this side, whatever solutions are on that side, and we put them together. An or means it's going to be either here or here. Either one is going to qualify for a solution. And is more restrictive. Any solution to this and this has to satisfy both at the same exact time. So that's a rundown of what's going on with compound inequalities. And it's the same kind of instructions. We still have to worry about whenever we divide by a negative number to change the sign. We're still going to be using the solution set in interval notation. Notice it doesn't say to write down a graph, but I still will write down that graph just for the sake of extra practice on how to get to the harder concept, interval notation. So that's what this section is all about. Kind of builds off the last one. They could have gone together, but sometimes it's nice to separate things out, make it more granular. Well, let's give this one a try for our first section here. When it comes to solving anything that's a compound inequality, the first strategy is divide and conquer. If there's two inequalities, you can just literally focus on one at a time and then move on to the next. That's how we're going to tackle this one with an and. And it's going to be pretty fast, right? We'll just start by subtracting 5. And that does it. X is alone, and this one will be solved. So subtract 5 from this side, subtract 5 from this side. We're not multiplying or dividing by a negative number, so the inequality direction does not change on this one. It stays as a greater than. So now we have x greater than, negative 3 minus 5 is now a negative 8. And we're done. We just do it all over again on this side right here, the right-hand side. This one looks like it takes a couple extra steps. First thing we want to do is remove that negative 5, so add 5 to both sides. So going left to right, we'll have negative 2x. It's a cancellation here, so we'll just say less than or equal to 6. Finally, we're dividing both sides by negative 2. That's the dangerous one. That's the one we look out for. And just to make this really apparent on the notes, if you come back here as a reference, it's a good idea to just write it down again, because if I go divide by negative 2 here, divide by negative 2 here, already this is wrong. It has to change directions the moment you divide by negative 2. So it's already changed to a greater than or equals to. That deserves another reminder. Flip sign when dividing. We're often dividing, but it's good to say the full statement, dividing or even multiplying by a negative. And I said sign. I think you could say that. That's an inequality sign, but I think it makes more sense to say flip the direction. In other words, we're flipping the direction of the inequality sign. I think that makes a little bit more sense in our heads. We say it that way. So left-hand side, negative 2 divides negative 2, so full cancellation. We already flipped the sign, so we're just copying it in. And negative 2 goes into 6, negative 3 times. And so that's all there is to say. We can now paraphrase by saying x bigger than negative 8 and x is greater than negative 3. So these are two conditions that have to be satisfied all at the same time. Our goal is to write our answer in interval notation here above. First, any questions at all, folks, getting to this stage? Okay, we're starting out with the and statement first because this one is honestly a little bit more tricky. Some people are very good at visualizing this. If I have to be bigger than or bigger than -8 and bigger than or equal to -3, some people can just see that interval notation just immediately in their head. If you're like me, a picture might be more valuable than just trying to visualize a whole bunch of moving parts in your head all at once. So this would be my strategy for every time an and compound equality comes up. I'm going to write down the graph for each one of these in turn. X greater than -8. Put a little colon here to say to the right of that is going to be its graph. I'll put -8 pretty far to the left this time because I'm also going to count off to -3 going to the right on the other one. But first, let's do the typical things that we did in the last section, 2.5. A strictly greater than, at this point in the wrong direction, going this way, means an open circle here. And then we shade to the right, which means I just sort of scribble for a moment while you all watch. It's probably easier to do this on a real pen, with a real pen or pencil. So that was the first condition. Linking them up are the and x greater than or equal to -3. So a little colon here just says this is what the graph looks like for this one. And I want to carry this down, keeping where the tick marks are, where the position is for -8, as carefully as possible. So here's where -8 was. This is one of those rare times I'm actually going to count off to -3. So -7, -6, -5, -4, -3. I just need to really visually see where that's at. This one is a solid dot because it says greater than or equals to. So solid dot here, and shade to the right again. So this and condition that's in the middle that we keep highlighting in yellow because it's, again, the major new thing in this section, is saying I want to have value x that is in both of the sets at the same exact time. In other words, the big concept here is the following. The overlap due to the and statement is where the solutions are. So if I picked a random number, oh, and I do spot an error. That should have said a -3. I wrote down a +3 there. So if you did as me, sorry about that. Make sure there's a negative sign for extra clarity. And what I was going to say is if you picked a random number, like say, this tick mark is -2, it satisfies that inequality, bigger than -3. And up here, it satisfies this inequality, it's bigger than -8. So it satisfies both at once. That means -2 way out here is a solution. And what I mean by overlap is we go up and down directly, it's in both sets. If you picked a number, say, like this one, -8, -7, -6 right here, -6 right where the red dot is not a solution to that bottom inequality. It's just not even in the shaded region. That's what the shading is meant to say. It's part of the solutions. Sure, it satisfies this one. It is in the solution set of x greater than -8. Let me put it up here just for emphasis. But that's not good enough. If there's an and statement, we need to take the numbers that solve both at one inequality and the second one all at the same time. So where that starts is right at -3. And that's what we mean by saying the overlap. -3 is in both sets, and every number to the right of -3 is in both sets. So we can say overall, once and for all, the solution set is this. One more graph just to visually emphasize how we're grabbing this. We go to -3, maintain the solid dot, shade everything going off to the right towards infinity. And just a couple dashed lines to convey this is where this was all overlapping. We did a lot of work on this one. We had to solve two inequalities. So it's like two problems in section 2.5 just duct taped together. Then we had to deal with two number lines. We had to analyze them to find where they both overlap all at once. And we're still not done. We want interval notation. But the good news is we're just about there. Once we get to describing the overlap, the interval notation goes bracket, close bracket, at -3, comma, going off to the right at infinity. So this is the set of numbers that satisfies both of these original inequalities way up above. A lot of work on this one, but again, the end is the harder one of the batch. When we do the OR versions, they're not as bad. Any questions at the moment, folks, getting through this one? Okay, let's try this all out on the next version. There's two versions of problems here. We'll do another AND version just for the sake of the extra practice. But this one is kind of the nicer version, the one with OR in the middle. So with the OR one, we take the same strategy as before. We're going to solve both inequalities independently, but whatever solutions we get here and whatever solutions we get here, we just put them together. So we don't have to look at where they might overlap or anything weird like that. We're just literally giving a total set of solutions. So let's give this a try. This one's already a little bit weird because the variable is A, but it could be A, U, V, W, X, P, anything along those lines. Let me recopy this one just so we can visualize it when we get started. 3/4 A minus 2 greater than or equals to 4. And strategies on this one, even though it has a denominator, I wouldn't clear the denominator on this one. If there's only one denominator right by the variable, easier to just add 2 to both sides and go from there. So start with add 2, add 2. Now 3/4 A is greater than or equal to 6. At this stage, you want to divide by 3/4, but there's a faster way to do that. You can just multiply both sides by 4/3, using a different color so it doesn't get too visually overwhelming. So division by 3/4 means literally multiply by the reciprocal. So just flip the fraction and multiply. Ensure you do it on both sides and you're all set. And the reason we do that is all of this stuff is canceled on the left-hand side. You can cancel like factors from numerator to denominator. It leaves behind just A greater than or equal to. You might take 6 times 4 for 24 divided by 3, but a lot of times it's simpler to just reduce here as well. 3 goes into itself once, into 6 twice. Far easier to just take 2 by 4 to get an 8, since that requires no reduction anymore. So that's the first one down. All we do is rinse and repeat, same thing on this one. Let's recopy it. 4 times 2 minus A greater than 0. Same kind of process. And I think a lot of people would tackle this slightly differently. Some people might use the distributive law, distribute 4 inside to get 8 minus 4A. Totally works and it's just fine. But you don't have to. Here's another way to go. You could just divide it by 4 right here as it stands. Another nice thing about these denominators and fractions is if there's a grouping symbol here, that means there's a little literal multiplication between these. And you can cancel these factors in this way. So divide by 4 means it just cancels completely off this one, leaving 2 minus A on the left. On the left. Greater than 0 divided by 4 is still just a 0. And so that's slightly easier to work with. And still, even on this line, I think a lot of people might do it differently. Some people might subtract 2, then divide by -1. Other people might just add A to both sides. Really up to you. Let's go with the add a to both sides. We have to pick a method. So here's what I would probably do. So right where the red dot is, negative a plus a cancels. It's just 2 left over, greater than a. We had a comment on this one already once. This might just feel awkward, but you can just flip the order. If you don't like 2 greater than a, you could just say a less than 2. The thought that you'd want to visually check is that the inequality arrow is still pointing at the same thing. It was pointing towards a, still pointing towards a down below, so it's the same idea. So we did it. Now, just to summarize, we have a is greater than or equal to 8, or a is less than 2. So that's the results of our hard work solving now 2 problems again, taped together with the OR statement. What we need is the interval notation solution to this. And if you're really pretty fresh on interval notation, you probably would go right to that step. If you're feeling a little bit rusty, that's why we'll do the graph, just to tie it all together. This is a good point to pause. Any questions at all, folks, so far? Okay, so here's what the graph is going to look like on this one. Just like in the last notes, I'm using blue for the graph and green for interval notation. We go and just start plotting these one at a time. A greater than or equal to 8, I'll place an 8 here. Because of the greater than or equal to, the or equal to puts in a solid dot. It's a way to say 8's included. And when we say a is greater than, it means shade to the right. So this is where one side of the solutions are, going off to infinity. But it's not the full story. We're either in here or we're in this set, less than 2. So we go off to wherever 2 is. Here we don't have to count them off. We can just place 2 somewhere on the graph, and that would be completely appropriate. Let me put it a little bit closer. It's a strictly less than sign, so this goes with the open circle, excluding 2. And now we shade just going off to the left in this direction, towards negative infinity. So that's the whole graph so far. This is a little bit different because when we go to interval notation, our solution sits in 2 pieces. It's either here, a less than 2 was here to here, or it's over here, a greater than or equal to 8 came to this side. You know, an arrow might not hurt to convey how these came together. So follow the arrows if that's helpful. But interval notation is always easy while you have the graph down. That's why I very, very often emphasize write down the graph to help out with this next step, because this is all you have to do. Start at the far left, negative infinity, comma, up to 2. 2 is not a solution, so we put an open parenthesis to match the open dot. Here's the new thing. The way we express OR whenever we're dealing with interval notation is through this symbol. It looks like a capital U, but U is just referred to as the union symbol. Union just meaning we're putting 2 things together. And union is always conflated with or at the same time. So we're reading this out as saying solutions are from negative infinity to 2, union or together with the set 8 off to infinity. This feels kind of weird to write. It's 8 and what looks like sideways 8, but that's just infinity to say everything larger than 8, never stopping. There's no largest number in that set, just like there's no smallest number in this set. Well, we did it, folks. This one is, in my opinion, not as bad as the last one. It has its own tricks to watch out for. And in these notes, it's all about being really careful between the ands versus the ors. If you're watching for those 2 different things, that'll help out a lot on these notes. And these sets of notes are good places to come back. If you're going to do exercises, you want a refresher, you can look over the problems that we did in these notes. The PDFs are always published here once the section's finalized. And so you can always refer back. I want to solve one more problem in these notes just to give another and version. It's the trickier one and show what other kinds of things can happen on these problems. But any questions at all, folks, after we've gotten through this one? Okay, let's go to the next one. Here's the last one in this whole section. It's another and statement, making it a compound inequality. We're highlighting in yellow kind of the worst part of these problems on every one of these problems. Weird that the variable is p, but again, it could be anything. It's just something to get used to. So two conditions, negative 5p minus 3 is greater than or equal to 2, and 4p minus 2 is greater than or equal to 5. Like before, really the first thing we do is we divide and conquer. Don't look at the entire thing, just look at one piece at a time. And by piece, we mean, let's just focus on that inequality here, following the arrow. Negative 5p minus 3 greater than or equal to 2. We start this one off by adding 3 to both sides. So now negative 5p is greater than or equal to 5. Another warning, we need to divide by negative 5, so we'll change the direction. I'll recopy just for emphasis to make it easier to spot on the notes when we do this kind of step. Divide by negative 5 here, negative 5 here. Now, right at that step, this has gone from a greater than or equals to into a less than or equals to. We won't write a comment every time that we do this, but it doesn't hurt to emphasize that one more time. That's all because of division by negative. And now p is less than or equal to -1. So halfway there. Rinse and repeat with the second inequality. So let's move this over in this direction. 4p minus 2 is greater than or equal to 5. Not as dangerous as a one to solve because we're going to divide by a positive 4 once we get to the solution. First, we wanted to add 2 to both sides. So now 4p is greater than or equal to 7. Then divide by 4. We get p greater than or equal to 7/4. Looks kind of awkward. It's an improper fraction, but it's in reduced form, so it's just fine as it stands. So we have two conditions on our solution set that we're looking for. We have to have, once I get this scrolled, there we go. We have to have p is less than or equal to -1, and all at the same time, p has to be greater than or equal to 7/4. That might seem kind of weird. If it doesn't seem weird yet, imagine what the picture is for this. To me, that's hard. It's hard for me to imagine all these graphs when I look at one or the other. So if you're like me, best thing to do is just write it down. It's great practice. The more you can write and be active, the easier it is to really learn and retain this kind of stuff. So we're going to recopy what we did on the very first example in these notes. If it's an and statement, you really want a separate number line for each part. So here's the first one. P less than or equal to -1. Let's put the next one down as well. P greater than or equal to 7/4. I think it might actually be easier to put both the number lines down first so that things line up better when you're starting to put down the actual tick marks and numbers. So now first is -1 here. This one comes in as a solid dot because of this less than or equals to. And I just want -1 to be copied down as well, just for reference. So now where we put the solid dot, because of the less than or equals direction, we'll shade to the left on this one. Towards -infinity. Could barely fit that one in. And improper fractions kind of rough on this, but if it was 8/4, that would have reduced to 2. So it's just short of 2, just barely to the left of it. So now on this number line here, here's -1, here's 0, here's 1, here's 2 out here, meaning 7/4 is about at that location. Put a little line there for 7/4. Straight up above, just for reference, here's 7/4 again. This is a greater than or equals, so a solid dot on this one. And for this one, we're asked to shade to the right, since P is greater than 7/4. Means all numbers to the right of 7/4, off to infinity. Now, because of the and statement, let's reduplicate this comment. The solution set is the overlap, but it's different this time, but there is none. There's no overlap with what's over here versus what's over here. They're in different parts. Let's scroll for just a moment to think about this. It's kind of like this one. These were in different parts, but this is a different problem. We were saying you're either here or you're in here. We'll take solutions from both. When you say and, it's got to look like this, like a shadow comes down and shows you where they overlap. That's the solution set. So if it ever looks like this one in our problem, nothing's overlapping when we let it project down, or imagine a shadow below. Nothing's overlapping here when we go upwards, or imagine a shadow being cast right over here from that solid line. So that tells us in this problem, there are no solutions. It deserves an exclamation mark. Sometimes the answer to the problems is nothing. This is an impossible condition. There's no way to have this inequality hold at the same exact time, because of the and, as that inequality holding. So the whole compound inequality was just a lie from the very beginning. Kind of rooted away because we had to work really hard in both of these columns to really detect that. But sometimes that can happen in the homework as well. So I felt like we should do one ourselves. Well, we did it, folks. This is the wrap up on compound inequalities. It's meant to be just an add-on to the prior section, the original inequalities. The next section we're going to look into comes into 2 parts. Looks like we'll have time to start the first portion, and we'll finish it up when we come back on next class Thursday, and then move into finally chapter 3. Again, we're a little bit behind on the schedule. I guess I took a little bit of extra time introducing the course last week, but we'll be all right. As long as we keep being mindful, we'll get caught up without having to cram too much before the exam. Any last questions at all, folks, before we go to the next section notes? Okay, let's take a look at that next section then. Looking at the time we have, this one looks like it will be our last one for today. If we have to come back here to finish off the last problem or two, that would work out just fine as well. We're never going to try to rush through the notes. I don't think that's fair to anybody. It's hard to learn when people are rushing. So section 2.7 is about solving absolute value inequalities. And now you can see why the math department decided to break this up in the Newton homework system. Part 1 is absolute value equations. So it doesn't even really fit the title of the section. An equation is not an inequality, but it's a good preliminary material before we get into section 2.7. Let's take just a preview of what section 2.7 looks like. In section 2.7, we're essentially doing this first part right here, where the red dot is. This is the absolute value equality because it's an equation. And the graph of the solutions are pretty basic. We often won't graph them. It's just 2 numbers. Sometimes it's 1, sometimes it could possibly be none, but most often than not, it'll be 2 numbers. Section 2.7, we actually do the inequalities finally. Yeah, this is kind of strange in a way. There'll be 2 kinds, where there's a greater than Notice our or statement comes in, so this is relevant to what we just did in the last section. A less than statement comes in. This is like the and statement, but since the solutions always look like this, we'll often just leave it in that form and not have to work as hard. So that's what we're going for, starting with the equality version first. Example 1 is kind of a preliminary example, just getting the feel for this new section. Then in examples part D and example 2, we start to solve some of the bigger problems that you're going to see in the notes. So starting off with a warm-up and then moving into the harder ones. First thing we should take a look at is just the overall formula for this section. It says, for any algebraic expression u. So that could be a number, that could be a variable like 2x, anything along those lines. And any positive real number a, already this is kind of confusing because there's lots going on. So let's track this with color coding. For any algebraic expression u, this is what goes inside the absolute value bars. And any positive real number a, this is going to be on the right-hand side. We can solve this absolute value equation by just splitting it up into two. The absolute value of u equals a, then either u is negative a or u is positive a. Let's in fact do an even simpler example down below just to kind of illustrate this. So here's my quick example to illustrate the formula above. So let's say absolute value of x equals 3. Well, let's recall what we mean by absolute value. Absolute value is just the distance from a number to 0 on the real number line. So if you do absolute value of negative 7, this one comes out to a positive 7. The reason for that is on the number line, here's 0, 1, 2, 3, 4, 5, 6, 7. Here's negative 7. And the absolute value is the distance. Equals 7. It's a directed distance. It doesn't matter if you went left or right. It's just how many tick marks are you away from the number 0. So we say absolute value of negative 7 is a positive 7 because of that distance. A lot of people like to think of it in this way. Whatever the number is, we take off the negative sign. Just know that absolute value bars are like order of operations. You have to do everything on the inside first. And so if you see something like, say, that one, absolute value of 9a minus 1, that negative sign doesn't go away. It's unfortunate because order of operations comes first. You actually have to do 9 times a, then reduce it by 1. But you can't even do that until you know what a is. So we're kind of stuck. That's why we have to have a formula like this one that directs us in those sort of cases when there's a variable on the inside. So the format says the absolute value of u equals a, then u equals negative a or positive a. In this example, if absolute value of x equals 3, then x equals negative 3, or x equals 3. And that makes sense because if you plug negative 3 back inside absolute values, absolute value of negative 3 is just back to positive 3. And absolute value of positive 3 thrown back in there checks as well as just 3 equals 3. So that's the name of the game for this kind of problem. Any questions at all, folks, with the discussion on the formula? Okay, so here's how these kind of problems go. Example 1, it's kind of a warm-up like we mentioned, and they're kind of fun in a way. It's, again, just divide and conquer. If it says absolute value of 2x equals 7, you just write down the 2x. It's playing the role of u inside here. It's going to be equal to negative 7, playing the role of 7 here. Oh, and I was supposed to highlight that, not scribble it. Or 2x, that's playing the role of u over here again. Equals positive 7. In other words, Another way to think about this is you just write down two equations now. One equation has the negative version of whatever is over here. The other equation has the positive version, and then you're all set. We just have to solve both of those. Both of them are solved in the same way. We just divide by 2. So on this one, x is less than -7/2 when we divide 2 out. Divide by 2 on this one, x equals 7/2 as well. And we're done. Those are both of the solutions. Kind of nice in the way. We've solved slightly harder problems in the next section, I would say, so far already. When you're putting in your answers in Newton, oftentimes you're just having a box with things that you separate with a comma. So you put in -7/2 first, and then 7/2 here. If this was what it looked like on an exam, it'd be totally fine just in this format. Some people might want to put in the or in between just to say I have two solutions. It's either this one or this one. And oftentimes people paraphrase the whole statement by writing -7/2, comma, 7/2. Lots of other shorthands, but these are the main ones. I oftentimes write my solutions out like this, since that's usually the format you would put in the answers in the Newton homework system. Just makes the homework look a lot more familiar with the notes itself. We did it, folks. There's two solutions, -7/2, +7/2. Part B is different, though. Notice it said for any algebraic expression u, so really anything goes inside that absolute values. But for a positive real number a, we have those two equations we solve. That's not a positive number, that's a negative. So watch out for something like this. If you're solving an absolute value equation, like we mentioned above here, the output could be 0 in absolute value, but that's only if you put absolute value of 0. That's the smallest it ever goes. For every other number you throw inside the absolute value function, you're getting something positive out. So the moment the equation says the absolute value of something comes out as a negative, it's a lie just immediately. So the whole point of this problem is, watch out for this one. It's a trick question, but the moment you spot the trick, it's really just a freebie in a real sense. No solution? Because of the negative sign. So that's one trick question to watch out for. Again, it's a freebie when you spot it, making it kind of nice in a way. And it's only valid for this right-hand side because the absolute value of anything can never be negative. Any questions with either two of those so far? Okay, part C is not a trick question. It's just a little bit weird. In fact, it doesn't feel like it even fits this because this says for any positive real number a, you have these two equations here and here. Well, a nice fun fact about math, 0 is not a positive number, it's not a negative number, it's the number in between. It doesn't have a sign whatsoever. Nonetheless, when you come up with these are kind of a nice problem. The solution is just simply x equals 0. It has one and only one unique solution to this, and that's because the absolute value of 0 is 0. By the way, you want to write your absolute value bars kind of tall, maybe bold, so it doesn't look like you're writing down something that might look like LOL or anything like that. It's kind of hard to do in the notes. Just do your best. So absolute value of 0 checks as 0. And that's the only solution to this one. So these are the warm-up kind of problems in this homework set so far. Any questions at the moment, folks, before we try a couple more and call it a day? Okay, so here's the big one in the set. And this is a pretty typical kind of problem. It's not too different as if you're dealing with an ordinary equation, except that it has an absolute value bar. Other problem is, because we're working with this idea right here, let me take a quick screenshot for us. there really is one preliminary step before we even get started. So here's the fundamental formula we're about to use above, coming from the start of the notes. And the idea here is step one, isolate the absolute value, let me spell that more appropriately, part. In other words, this formula only holds if the portion absolute values, that's this part right here, is completely isolated on one side of the equation. So that implies we have a little bit of preliminary algebra to do on this one before we even use this formula above. Well, it's not too bad. If we want to get the absolute value part alone, just start off by subtracting 6 from both sides. So here's minus 6 from both sides. We have negative 2 times the absolute value, 4w plus 1, close absolute value, equals negative 12. And notice we're not worried too much about the negative sign here because it's still not something like this one that had no solution. Here, absolute value was isolated and we had a negative on the right, so we just got to stop. Assert no solution, and our job was done on that one. But this absolute value is still not isolated. This is not the full story. You still need to divide by negative 2 to really see what happens next. So divide both sides by negative 2. We have a cancellation here on the left going this way. And the negative sign cancels. On the right, the negative signs cancel as well, and we just get 6. Comes out positive, which means we do have solutions on this one. So absolute value 4w plus w, 4w plus 1 equals positive 6. So now we have an arbitrary algebraic expression playing the role of u is this time 4w plus 1, highlighted in green. The right-hand side is a positive real number, so we do this step. It just splits into 2 equations. So here's the split them up step. 4w plus 1 is equal to, I usually put in my negative number first, but that's totally up to you. Let me put in negative 6. Or our ors match up in this way. 4w plus 1 equals positive 6. So not too bad. How we exchanged a pretty tough looking absolute value inequality, isolated it, then it splits into 2. It's like a hydra. Now we have 2 ordinary equations. So this is the relaxing part of class. We'll make this one our last problem of the day. Just do the normal things you would algebraically. Subtract 1 from both sides on this one. I'll do them just one at a time. Or w equals negative 7. Last, divide by 4 on both sides. W equals negative 7/4. So that's 1 down. Then just duplicate those steps. Subtract 1. 4w is equal to 5. Divide by 4. W equals 5/4. So lots of ways to write your answers. I have 2 answers. This time I'm just going to box them up. So if you feel like your stuff is kind of a little bit out of line, maybe a little bit all over the place, that's a pretty good time to box your answers. Or you could have wrote a third line that looked like this, just restate them to say, these are my official answers, there's nothing left. And honestly, if this was an exam question and you just left it like this, I can tell where your answers are. I would just assume you're running short on time, you're just moving on to the next problem, and sometimes that is a great strategy. But we did it, folks. We moved through 3 sections. We're mostly done through section 2.7. When we come back next class on Thursday, we'll finish off these notes, the part 2 of these notes, and begin moving through section 3.1. But any last questions at all, folks, before we call it a night? Well, have an excellent evening, everyone. We'll be right back here on, looks like example 2 next class. Talk to you all later.